BX cable or armored cable typically includes a small bare copper grounding wire. However, in older installations, this wire might be absent or inadequately sized for modern grounding standards. Outdoor electrical installations, especially those involving metal components like lamp posts, demand proper grounding to protect against electrical shocks and ensure safe operation. Firstly, let's discuss inspecting the BX cable ground. The first step is to identify the junction box where the BX cable and underground feeder cable connect. Secondly, check if the BX cable has a bare copper grounding wire. If it does, proceed to the third step. Thirdly, measure the diameter of the grounding wire. For a maximum circuit current of 20 amps, it should be at least American wire gauge number 12, which is 2.5 millimeters. If it is smaller than American wire gauge number 12, it might not provide adequate grounding. Now let's discuss the alternative, which involves installing a ground rod. If the BX cable grounding wire is absent or undersized, a separate ground rod can be installed at the junction box to provide the necessary grounding. First step is to locate a suitable location for the ground rod, preferably near the junction box. Secondly, drive an 8-foot copper-clad ground rod into the ground. Thirdly, connect the grounding wire from the junction box to the ground rod using a ground rod clamp. In conclusion, if the BX cable has a properly sized grounding wire, American wire gauge number 12 or larger, it may provide an acceptable ground for the outdoor installation. However, if the grounding wire is not present or is undersized, installing a separate ground rod at the junction box is recommended. This will ensure proper grounding and safety for the outdoor electrical installation. Ensuring safety in electrical installations is crucial. Grounding is a critical aspect of electrical safety, designed to protect individuals from electrical shock and to ensure the proper operation of electrical devices. The National Electrical Code, or NEC, provides detailed guidelines for grounding and bonding electrical systems. When working with electrical systems, it is imperative to adhere to these guidelines to mitigate risks. The purpose of a grounding system is to provide a low impedance path for fault current to return to the source. This path facilitates the rapid operation of overcurrent protective devices such as circuit breakers or fuses in the event of a ground fault. Without an effective grounding system, fault currents may persist, posing a significant electrical shock hazard. Grounding also helps to stabilize voltage to ground during normal operation, reducing electrical noise and improving the performance of sensitive electronic equipment. Several methods exist for grounding electrical systems, and the selection of the appropriate method depends on various factors, including the type of system, the size of the load, and the environmental conditions. One common method involves using a grounding electrode system, which typically consists of one or more ground rods, ground plates, or underground metallic water pipes that are connected to the electrical system. The grounding electrode system provides a direct connection to the earth, ensuring a low impedance path for fault current. Another method involves using a separately derived system, such as a generator or transformer, to supply power to a specific load. In this case, the grounding electrode system is connected to the separately derived system, providing a dedicated ground for the load. Bonding is another essential aspect of electrical safety. Bonding involves connecting all non-current carrying metal parts of an electrical system together to create a common ground potential. This includes metal enclosures, conduit, and equipment frames. By bonding these components together, any fault current will have a low impedance path to ground, minimizing the risk of electrical shock. The National Electrical Code, or NEC, specifies the minimum size requirements for grounding and bonding conductors. These requirements are based on the size of the overcurrent protective device protecting the circuit. It is crucial to adhere to these requirements to ensure the effectiveness of the grounding and bonding system. Regular inspection and maintenance of grounding and bonding systems are essential to ensure their continued effectiveness. Over time, corrosion or physical damage can compromise the integrity of grounding and bonding connections, increasing the risk of electrical shock. It is recommended to periodically inspect grounding and bonding connections and to repair or replace any damaged components. When working with electrical systems, it is always advisable to consult with a qualified electrician to ensure that the grounding and bonding system is properly installed and maintained. A qualified electrician has the knowledge and experience to identify potential hazards and to implement appropriate safety measures. Understanding the principles of grounding and bonding is essential for anyone working with electrical systems. By following the guidelines provided in the National Electrical Code, or NEC, and by taking appropriate safety precautions, it is possible to minimize the risk of electrical shock and to ensure the safe operation of electrical equipment. Remember that electrical work can be dangerous, and it is always best to err on the side of caution. If you are not comfortable working with electrical systems, seek the assistance of a qualified electrician. Understanding the NEC tables related to grounding and bonding is essential for electrical professionals. These tables provide specific requirements for conductor sizes, grounding electrode conductor sizes, and other critical aspects of grounding and bonding systems. For example, NEC Table 250.122 provides the minimum size of equipment grounding conductors for grounding raceway and equipment. The size of the equipment grounding conductor is based on the rating of the overcurrent protective device protecting the circuit. It is important to select the correct conductor size to ensure that the grounding system can effectively carry fault current. Similarly, NEC Table 250.66 provides the minimum size of grounding electrode conductors for connecting grounding electrodes to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Again, it is essential to select the correct conductor size to ensure a low impedance path for fault current. NEC Table 310.16 provides the allowable ampacities of insulated conductors. This table is used to determine the appropriate size of conductors for various applications, including grounding and bonding conductors. The ampacity of a conductor is the maximum current that it can carry continuously under specific conditions without exceeding its temperature rating. When selecting conductors for grounding and bonding, it is important to consider the ampacity requirements to ensure that the conductors can safely carry fault current. In addition to these specific tables, the NEC contains numerous other provisions related to grounding and bonding. It is important to be familiar with these provisions and to apply them correctly when designing and installing electrical systems. Furthermore, local codes and regulations may impose additional requirements for grounding and bonding. It is crucial to comply with all applicable codes and regulations to ensure the safety and compliance of electrical installations. The National Electrical Code, or NEC, is updated every 3 years, so it is important to stay current with the latest edition. Changes to the NEC can affect grounding and bonding requirements, so it is essential to be aware of these changes. Continuing education courses and professional development opportunities can help electrical professionals stay up to date with the latest NEC requirements. Grounding electrodes play a crucial role in electrical safety by providing a direct connection to the earth. This connection ensures a low impedance path for fault current, allowing overcurrent protective devices to quickly trip and energize the circuit in the event of a ground fault. The National Electrical Code, or NEC, specifies the types of grounding electrodes that are permitted and the requirements for their installation. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground to a depth of at least 8 feet. Ground plates are typically made of copper or galvanized steel and are buried in the ground to a depth of at least 2.5 feet. Underground metallic water pipes can also be used as grounding electrodes, provided that they meet certain requirements. The NEC requires that the grounding electrode system have a resistance to ground of 25 ohms or less. If the resistance is higher than 25 ohms, an additional grounding electrode must be installed. The resistance to ground can be measured using a ground resistance tester. The NEC also specifies the requirements for grounding electrode conductors, which connect the grounding electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. It is important to select the correct conductor size to ensure a low impedance path for fault current. Proper installation of grounding electrodes is essential for their effectiveness. Ground rods should be driven vertically into the ground, and ground plates should be buried horizontally. The grounding electrode conductor should be securely connected to the grounding electrode using a suitable connector. Regular inspection and maintenance of grounding electrodes are important to ensure their continued effectiveness. Over time, corrosion or physical damage can compromise the integrity of grounding electrodes, increasing the risk of electrical shock. It is recommended to periodically inspect grounding electrodes and to repair or replace any damaged component. Understanding the requirements for grounding electrodes is essential for anyone working with electrical systems. By following the guidelines provided in the National Electrical Code, or NEC, and by taking appropriate safety precautions, it is possible to ensure the safe and effective grounding of electrical systems. Equipment grounding conductors and bonding jumpers are essential components of an electrical grounding system. They provide a low impedance path for fault current, allowing overcurrent protective devices to quickly trip and to energize the circuit in the event of a ground fault. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment, such as enclosures and equipment frames, to the grounding system. Bonding jumpers connect different metal parts of the electrical system together to create a common ground potential. A National Electrical Code, or NEC, specifies the requirements for equipment grounding conductors and bonding jumpers. The size of the equipment grounding conductor is based on the rating of the overcurrent protective device protecting the circuit. The size of the bonding jumper is based on the size of the largest ungrounded conductor in the circuit. It is important to select the correct conductor sizes to ensure that the grounding system can effectively carry fault current. Equipment grounding conductors and bonding jumpers must be made of copper or other approved materials. They must be securely connected to the equipment and the grounding system using suitable connectors. The NEC also specifies the requirements for the installation of equipment grounding conductors and bonding jumpers. Equipment grounding conductors must be run with the circuit conductors. Bonding jumpers must be installed in a manner that provides a low impedance path for fault current. Proper installation of equipment grounding conductors and bonding jumpers is essential for their effectiveness. Loose or corroded connections can increase the impedance of the grounding path, reducing its ability to carry fault current. It is recommended to periodically inspect equipment grounding conductors and bonding jumpers and to tighten or replace any loose or corroded connections. Understanding the requirements for equipment grounding conductors and bonding jumpers is essential for anyone working with the electrical systems. By following the guidelines provided in the National Electrical Code, or NEC, and by taking appropriate safety precautions, it is possible to ensure the safe and effective grounding of electrical equipment. In scenarios where existing grounding systems are inadequate, several methods can be employed to improve the grounding and bonding. These methods include installing additional grounding electrodes, upgrading grounding conductors, and improving bonding connections. Installing additional grounding electrodes can reduce the overall resistance to ground, providing a more effective path for fault current. The additional grounding electrodes should be installed in accordance with the National Electrical Code, or NEC, requirements. Upgrading grounding conductors can also improve the effectiveness of the grounding system. Larger grounding conductors have a lower impedance, allowing them to carry more fault current. The size of the grounding conductors should be selected based on the rating of the overcurrent protective device protecting the circuit. Improving bonding connections can also enhance the grounding system. Loose or corroded bonding connections can increase the impedance of the grounding path, reducing its ability to carry fault current. Bonding connections should be inspected periodically and tightened or replaced as necessary. In some cases, it may be necessary to install a new grounding system to address inadequate grounding. This may involve installing a new grounding electrode system, upgrading grounding conductors, and improving bonding connections. The design and installation of a new grounding system should be performed by a qualified electrician. When improving grounding and bonding, it is important to consider the specific needs of the electrical system. Factors such as the type of equipment being grounded, the size of the load, and the environmental conditions should be taken into account. It is also important to comply with all applicable codes and regulations. Improving grounding and bonding can significantly enhance electrical safety. By providing a more effective path for fault current, these improvements can reduce the risk of electrical shock and equipment damage. Regular inspection and maintenance of grounding and bonding systems are essential to ensure their continued effectiveness. Understanding the methods for improving grounding and bonding is essential for anyone working with electrical systems. By following the guidelines provided in the National Electrical Code, or NEC, and by taking appropriate safety precautions, it is possible to ensure the safe and effective grounding of electrical systems. Addressing common grounding and bonding mistakes is crucial for maintaining electrical safety. One common mistake is using undersized grounding conductors. The National Electrical Code, or NEC, specifies the minimum size requirements for grounding conductors based on the size of the overcurrent protective device protecting the circuit. Using undersized grounding conductors can reduce the effectiveness of the grounding system, increasing the risk of electrical shock. Another common mistake is neglecting to bond metal enclosures and equipment frames. Bonding ensures that all non-current carrying metal parts of the electrical system are at the same potential, minimizing the risk of electrical shock. All metal enclosures and equipment frames should be properly bonded to the grounding system. Another common mistake is making improper grounding connections. Grounding connections must be secure and corrosion resistant to ensure a low impedance path for fault current. Loose or corroded connections can increase the impedance of the grounding path, reducing its ability to carry fault current. Another common mistake is failing to test the grounding system. The National Electrical Code, or NEC, requires that the grounding system be tested to ensure that it meets the resistance requirements. Testing the grounding system can identify potential problems, such as loose connections or corroded electrodes. Another common mistake is using improper grounding electrodes. The NEC specifies the types of grounding electrodes that are permitted and the requirements for their installation. Using improper grounding electrodes can reduce the effectiveness of the grounding system. Avoiding these common grounding and bonding mistakes can significantly enhance electrical safety. By following the guidelines provided in the National Electrical Code, or NEC, and by taking appropriate safety precautions, it is possible to ensure the safe and effective grounding of electrical systems. Regular inspection and maintenance of grounding and bonding systems are essential to identify and correct any mistakes. Surge protection devices, or SPDs, play a vital role in protecting electrical equipment from voltage surges. Voltage surges can damage or destroy sensitive electronic equipment, leading to costly repairs or replacements. SPD are designed to limit the voltage that is applied to electrical equipment, diverting excess current to ground. The National Electrical Code, or NEC, requires the installation of SPD in certain applications. SPD are typically installed at the service entrance, at distribution panels, and at individual pieces of equipment. SPD are available in a variety of types and ratings. The type of SPD that is appropriate for a particular application depends on the voltage and current levels that are expected. The rating of the SPD indicates the maximum surge current that it can withstand. When selecting an SPD, it is important to consider the surge current rating, the voltage rating, and the type of equipment that is being protected. SPD should be installed by a qualified electrician. Proper installation is essential for the effectiveness of the SPD. SPD should be installed in accordance with the manufacturer's instructions and the National Electrical Code, or NEC, requirements. Regular inspection and maintenance of SPD are important to ensure their continued effectiveness. SPD can degrade over time, reducing their ability to protect equipment from voltage surges. SPD should be inspected periodically and replaced as necessary. Understanding the role of surge protection devices, or SPDs, is essential for protecting electrical equipment from voltage surges. By selecting and installing SPD properly, it is possible to minimize the risk of equipment damage and downtime. GFCI protection is a critical safety measure designed to protect individuals from electrical shock. Ground fault circuit interrupters, or GFCIs, are devices that monitor the current flowing in a circuit and quickly interrupt the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are designed to trip within milliseconds of detecting a ground fault, preventing serious injury or death. The National Electrical Code, or NEC, requires GFCI protection in certain areas such as bathrooms, kitchens, and outdoor locations. GFCIs are typically installed in receptacles or circuit breakers. GFCI receptacles have a test button and a reset button. The test button should be used periodically to ensure that the GFCI is functioning properly. If the GFCI does not trip when the test button is pressed, it should be replaced. GFCI circuit breakers provide GFCI protection for an entire circuit. They are typically installed in the electrical panel. GFCI circuit breakers also have a test button that should be used periodically. Regular testing of GFCIs is essential to ensure their continued effectiveness. GFCIs can save lives by preventing electrical shock. Understanding the role of GFCI protection is essential for electrical safety. By installing and testing GFCIs properly, it is possible to minimize the risk of electrical shock. Aluminum wiring connections require special attention to ensure safe and reliable electrical connections. Aluminum wiring was commonly used in homes built in the 1960s and 1970s. However, aluminum wiring can be prone to loosening and overheating, which can create a fire hazard. When working with aluminum wiring, it is important to use special connectors that are designed for use with aluminum. These connectors are typically made of aluminum or copper-aluminum alloy. They are designed to provide a secure and corrosion-resistant connection. Antioxidant compounds should be used on all aluminum wiring connections. Antioxidant compounds help to prevent corrosion and improve the conductivity of the connection. The connections should be properly tightened to ensure a secure connection. Loose connections can cause overheating and create a fire hazard. Regular inspection of aluminum wiring connections is important to ensure that they are in good condition. Loose or corroded connections should be tightened or replaced. In some cases, it may be necessary to replace aluminum wiring with copper wiring. Copper wiring is more reliable and less prone to overheating. Replacing aluminum wiring with copper wiring is a significant undertaking and should be performed by a qualified electrician. Understanding the special considerations for aluminum wiring connections is essential for electrical safety. By using proper connectors, antioxidant compounds, and regular inspection, it is possible to minimize the risk of fire. Electrical safety audits and inspections play a crucial role in identifying potential hazards and ensuring compliance with electrical codes. Electrical safety audits are comprehensive assessments of an electrical system. They are typically performed by qualified electricians or electrical inspectors. Electrical safety audits involve a visual inspection of the electrical system, as well as testing of electrical components. The purpose of an electrical safety audit is to identify any potential hazards, such as damaged wiring, loose connections, or overloaded circuits. Electrical inspections are typically performed by local building officials. Electrical inspections are required for new construction, renovations, and additions. The purpose of an electrical inspection is to ensure that the electrical system complies with all applicable codes and regulations. Both electrical safety audits and inspections are essential for maintaining electrical safety. They can help to identify potential hazards and ensure that the electrical system is safe and reliable. Regular electrical safety audits and inspections are recommended. The frequency of these audits and inspections will depend on the age and condition of the electrical system. Understanding the importance of electrical safety audits and inspections is essential for homeowners and business owners. By having regular audits and inspections performed, it is possible to minimize the risk of electrical hazards and ensure the safety of occupants.